Colonel Eric Felt is the director of the Air Force Research Laboratories Space Vehicles Directorate. Pete just talked about that group. And he's the commander of the Phillips Research Site, where he leads a team of more than 1,000 scientists, engineers, and support personnel. This hard-charging team, composed of mostly United States Space Force Guardians, is focused on satellite operations, space domain awareness, advanced space solar cells, and space exploration. Colonel Felt has his master's and doctorate degrees in electrical engineering and is a graduate of the U.S. Air Force Test Pilot School. Colonel Felt, the screen is yours.
Thank you, and good afternoon. I am so honored to be presenting to the Freedom Foundation for the Future today and to be a part of this conference. I was able to join for a couple hours yesterday, just found it truly inspirational. And in fact, it prompted me to go home last night and watch the first half of the High Frontier movie. Really good stuff, and I can't wait to finish the second half tonight, so please don't tell me how it ends. But really happy to be and honored to be a part of this event today, and to be thinking so strategically and so proactively about the future that we want to create, and how space solar power is the key foundation to that in my mind. So I'm also honored to be executing the SPIDR program for our United States Space Force. SPIDR is the program that the DoD is pursuing for space solar power effort, and really happy that we were chosen to be a part of that. It's an idea, as you know, that is not new. But the tech readiness and the need have kind of aligned now, so that I do think that we have an opportunity here. And that's, of course, the crux of what we're talking about at this conference here today. Now at AFRL, I'm fundamentally focused on deterring war. Okay, that's my mission. And so I work on the technologies to make sure that we don't have to go to war, especially a war in space, which would be very bad. So as we look at our portfolio, we look at how is this technology going to help us deter enemy aggression in 2030, say. And China and Russia are the main adversaries that we're focused on in terms of making sure that they don't see an opportunity to engage in war with us, especially in space. And so in that context, we look at the return on investment from all the various different technologies in which we could invest. And I've learned something very interesting over the past 2 years, and that is that the highest ROI in all these analyses comes from doing new stuff in space. It does not come from doing incremental improvements to the stuff that we're already doing. So we're going to continue to evolve and improve missile warning and GPS, but there are some really amazing opportunities in doing new missions in space, missions such as space solar power beaming. So that's why we're so interested in this and why we're so focused on this. SPIDR is now actually the largest program I have in the Directorate, with over $250 million over 5 years that we're going to invest here, which is not anywhere near what's needed to finish the technology, but it's going to get us to the next stepping stone that we need. And again, really honored to be able to be involved in that. Now, again, these are not necessarily new ideas. We talked yesterday about how Jerry O'Neill envisioned this stuff back in the early 70s, and now it's just that it's technologically possible to do this. So this is what in the category of in-space logistics, or OSAM as we call it, as an enabling technology to some of these future missions that I talked about. So if we're going to enable future missions, sometimes there's extra stuff we need to do, such as logistics, to be able to enable those. And so I look at OSAM and logistics and space power from the DoD lens of things, which is slightly different from the overall industry and national view of things that we've been talking about most of the time. I look at the military utility and the feasibility of it. And a couple things that I just want to mention from our DoD lens, we're really not pursuing human presence in space at this time. So we're looking to enable space missions that will be able to support our terrestrial warfighters and our terrestrial humans. Doesn't mean we won't at some point in the future, but I kind of have to subtract that out as a measure of military utility because that's not something we're looking at right now. And the other key thing that's a little bit different from our lens is that I'm very focused on the resiliency of our space capabilities and how I must increase the resiliency, not decrease the resiliency by creating more vulnerabilities for our space systems. So the way that manifests itself, for example, is that in general, we like small satellites and distributed architectures in space because it makes it a lot harder for the enemy to attack. We do not like large structures that are very vulnerable. So SPIDR, and you'll see this is a large structure in space that we're proposing, the resiliency aspect of it is very important to me in making sure that we can, from a DoD perspective, provide this capability in a resilient way. So those are sort of two nuances of the way the DoD looks at these topics as compared to the sort of industry and society in general. So with that introduction, let's go to the next slide, please. And so space solar power is one of the highest return on investments, long-term projects that we have underway right now. It meets a military need, which is basically what we call power on demand, the ability to deliver power wherever the military needs it. So you can imagine in Afghanistan, for example, we have forward operating bases. We have to bring in trucks of fuel oil to power the generators to run those forward operating bases. Those logistics lines and that trucking is subject to enemy attack and has to be defended. It is super attractive to be able to just put power wherever you need it, whenever you need it, immediately. So we call that power on demand, and that is the military need for this technology. That's why we have the funding to do this, and that's why we're pursuing this technology. Now, the great thing about this particular technology is that there's so many spillover societal benefits, and we've talked a lot about those, but and Peter Garrettson just summarized them very nicely, but the benefits to climate change, the benefits to the space economy are huge. So I love it when we can work on a military problem and yet envision how that technology is going to enable all these other residual benefits to society that'll come out of that. And that's exactly how I see space solar power. So while we work on the power on demand problem for the DoD, this will be maturing the technology that others need to take this to the next level and make this the space economy, the pillar that we envision for the future. To do that, of course, we welcome partnerships with NASA, the Space Corporation, and or the private sector. If I had to place my bets, I would bet on the private sector getting this stuff done faster than anybody else based on recent events. And it's really exciting to be able to see all that innovation coming out of the private sector. And so what I'm trying to do at AFRL is enable and encourage and partner to try to facilitate and make that happen in the most productive way possible. I already mentioned that SPIDR is my largest AFRL space program right now, and really I agree with Peter Garrettson that it is the biggest idea in space and in energy. So to be able to bring those two ideas together is something that's really powerful. I am concerned about Chinese domination of this technology and Chinese domination of space in general, and that could lead us to strategic surprise. So this is in a bad way, and so that's why this is such an important priority and interest for me. So let's talk about AFRL's approach. Next slide, please. What you'll find is that I'm really particularly proud of how the team has been able to look at this end capability that we need, power on demand, and then decompose it in a logical system engineering kind of way to what are the technical challenges that we need to tackle. How do we go after the hardest of those first so that we can fail fast or hopefully not fail? And then mature those technologies in a logical way. And so that's what we call our critical technology elements. And I again, feel like the team has done a very good job of identifying those and putting in place the paths we need to mature each of the critical technologies. I will tell you right now, do not see any showstoppers to making this work, but there's engineering work that needs to be done in a number of areas, and that's where the team is focused. The nice thing is we can do that engineering work in parallel development paths. And so what we've done is lay in at least 3 different space experiments that will mature those CTEs in logical ways that are not necessarily dependent on each other in the early phase. So that's I think a good approach on how to mature this technology. And then integrate those into prototypes that are going to over time get us to the very large structures that we need to realize the end vision for the DoD and the nation and the world. So that's the overall approach. We will describe it for you in a video here.
Ensuring that a forward operating base maintains reliable power is one of the most dangerous parts of military ground operations. Convoys and supply lines are a major target for adversaries. Ground-based solar, while seemingly an attractive solution, is limited by area, the size of collectors required, and climate. But if the solar panels were in orbit, they could have unfettered access to the sun's rays, providing an uninterrupted supply of energy. AFRL's Space Solar Power Incremental Demonstrations and Research, or SPIDR project, strives to develop a design concept that will collect solar energy using highly efficient photovoltaic cells. That solar energy will be converted into radio energy and beamed to a receiving station on Earth. It will then be converted back into power for use by the warfighter and other end users. Arachne, SPIDR's flagship experiment, is a small-scale vehicle which will demonstrate and validate 3 of the 5 critical technology elements that will need to be matured before a full-scale prototype can be built. Energy collection, RF beaming, and beam shaping and focusing, or metrology, will be developed and tested with Arachne. 2 other critical technologies, stowable and deployable structures for space vehicles, and thermal management of solar power collection in space, are also being pursued in parallel to the Arachne effort. These small-scale proof-of-principle prototypes lay the foundation for the development of a full-scale operational system. This project paves the way for a system that provides reliable power while eliminating the need for costly and dangerous convoys used to refuel generators in remote areas. Much like the global positioning system, this solar beaming system could transition from military to common use, providing solar energy regardless of weather, time of day, or latitude. AFRL, fast-tracking the science fiction of the past into the reality of the future.
It's exciting.
All right, that is a pretty motivational video in my mind. So thank you for enjoying that with me today. So why are we doing this now? What are the key enabling technologies? I summarized that a little bit here on slide 4. Again, we may, Jerry envisioned this back in the early 70s, but it just at that time would have been much more expensive than it is now. So I now think this is very feasible. The first key enabling technology that has been matured a lot recently is these deployable structures. And these deployable structures are needed because in order to get a 10,000 square meter blanket in space, which is how you can envision this particular satellite, you're going to need to both assemble in space and deploy once you get there. So maybe you can fold up your blanket and launch it and deploy it. It's still not going to be 10,000 square meters. So you need both the deployable structures once you get up there and the assembly in space to envision the 10,000 square meter blanket that we want to get to. We've made tremendous advances in that. You've now got antennas that routinely deploy in space, even to very large sizes, and that technology is ready to go. Increased efficiency of the electronics. So the problem is that if your electronics are not efficient enough, and then you end up converting a lot of the solar energy into heat rather than re-radiating it out the other side of the blanket. And of course, that is a problem. The heat dissipation, it can be a problem. So the more efficient you are and the more efficient you can make your analog electronics there, the better off you're going to be. We've now reached the point where we think we can make it work. Reduced mass and high efficiency solar cells. Again, when you're talking about 10,000 square meters, you got to make sure that these things are very efficient, very mass producible, and low cost. And we have reached the point in solar cell development where we think we're there to make that work. Low cost manufacturing, both on the ground and in space. In order to produce these large structures, you need space to just be a commodity item that comes off the assembly line. That's exactly what we're getting to with these commercial mega constellations that are going up now. Finally, space is not some kind of exquisite one-off thing that you're building each satellite on its own, but rather you can practice all the benefits of mass manufacturing. Finally, Elon Musk there has certainly lowered the cost per kilogram to get to orbit, under $1,000 now and going even lower, is a super key enabler of making this work. Because when you have to put that much mass up there to build your structure, the cost to get to orbit was a barrier for decades that has now fallen. So that's really key. And then the last one is what we're working on. And so that is this solar to RF sandwich module, which we believe is a potentially game-changing technology that doesn't make you have to store the energy. You just bring solar in one side, RF out the other, and you're good to go. So that is the key thing that we're going to demonstrate, a 1 square meter technology demonstrator here in the next 3 years. And then from that, you'll be able to build out to the 1,000 and then the 10,000 square meter blankets that we eventually need. So we think we can get there. I don't see any showstoppers. These are the key technologies that let us do this now, even though it was very expensive and time, perhaps not feasible in the past. Next. So our role is to set up this project that we call SPIDR, and you just saw the video on it. And again, it will culminate in a space-based demonstration that breaks the 1 meter square barrier of the basic technology that's needed. That includes the thermal technology, the metrology to know where your blanket is and adjust your transmission so that you can aim the beam to be exactly where you need it to be. And that will then, when scaled, enable you to transmit power to a rectifying antenna at a forward operating base. And how much power? 1,000 kilowatts is the design goal for now. Again, once you get this to a scalable technology, there's no limit as to what you could be able to do. Now, that's a big step. So we've got a series of incremental demonstrations along the way that will get us there with these key critical technology elements. Next. So what are those critical steps along the way? The left gray box, the solar to RF sandwich module, is the focus of our immediate effort. We've got this working on a less than 1 square meter sandwich module on the ground now. What we're building that up into is to a larger than 1 square meter panel of tiles that we will then launch into LEO and show that this can in fact beam power to the ground. And with this amount of power, I will be able to light up a tiny little LED, but at least prove out the basic concept. And again, once you have that, then you can scale. The next step, we believe, is what we call the Scorpion spacecraft, which will be 1,000 square meters, which again does not get us to the end state, but it's a good next step in terms of scaling. It'll get you about 100 kilowatts that you can beam to the ground, and you'll have another set of technology challenges managing that large of a blanket, as we call it, up in space. And then from there, you'll be able to get to the 10,000 square meters and the 1,000 kilowatts, which is what we need to power the forward operating base. So it's kind of a 4 order of magnitude effort, and we've laid in what we believe is a logical progression of the technology that over time we will work with NRL, NASA, other players in the field to hopefully get there. Next. So we talked a little bit about the integrated demonstrations, and I have focused a lot on what we call Arachne, which is the demonstration of the sandwich module, the solar to RF panel. That again, going to launch that in 24. It will be able to power a little LED, but prove out all the key enabling technologies. That is the first of the integrated demonstrations. The other 2 that are pictured here on the slide are along the lines of maturing the critical technology elements. So one of those is called spiral, and that gets after the thermal issue. So again, we want to maximize the efficiency of the solar panel, maximize the efficiency of the electronics so that you minimize the heat generation. But the problem remains that we're going to have a heat problem. And sometimes the blanket's too hot, sometimes the blanket's too cold. But we are at AFRL, we have a lot of expertise in thermal management, and we are applying all of a number of different ideas for how to best do that, whether it's variable emissivity materials or new kinds of oscillating heat pipes, all kinds of different possible thermal management ideas applied there. And those will be tested out on Spiral, on the International Space Station, and on other in-space assets to mature the needed thermal technology. And then the other key thing, near-term demonstrator that we have is a deployable structure that's also going to be put into LEO called Spindle. And there are a number of different technologies you can imagine for how you're going to pack the blanket and then stretch the blanket out after you get onto orbit. We are maturing those ideas with ground testing right now, and we are going to eventually launch the winner of those concepts up into an on-orbit demonstration that we call Spindle. It'll get the TRL of the deployable structure up to where we need it to be for the next stage of development. So again, this is one of the things that I think AFRL has been able to add a lot of value to this process of, once you have the vision, once you know where you are today, what's the logical step in technology maturation to get there, and how can we help do that with our SPIDR program? And so progressing along each of the steps needed for technology development, focusing on the hardest stuff first so that we can fail fast if that's where we end up. But again, I don't think that's where we're going to end up. I think we can do this, and I think now's the time to do it. And I think there's going to be huge benefits to the DoD and eventually to the nation and the world from maturing this technology. It really is some low-hanging fruit that's out there, and we are honored and excited to be doing our part in this grander vision of how to mature this technology as a pillar of the future space economy. With that, is that my last slide, Ben? Yep. Okay, so I have a couple of minutes left for questions. Eager to talk to you about anything you'd like.
This is great. I can see why you're in charge of such a large staff. Every time I came up with a question, you answered it on the next slide, all in order. Really well done. I appreciate it. Talk a little bit about you opened with concerns about China becoming a leader here. With the timelines that you've set forth for the various tests and incremental growth of the SPIDR program, do you see us being first? Do you see the United States being first with those projects, or do you still think there's some open-endedness about who's going to get there first at that scale?
I think there's a lot of open-endedness. In fact, I think the Chinese have been a lot more proactive about recognizing this opportunity, laying it in as a strategic vision. If you go to conferences on this topic, you will see Chinese presenters with a very good strategig vision over the next 15 to 20 years of how they're going to get there with this technology. Honestly, I don't really see the interest or the maturity of the planning on our side to that level. So that's why I'm concerned. I think they have recognized this opportunity and started to move out on it. Where I think we have an advantage is that we still do have a great entrepreneurial spirit. We have the strongest commercial space companies. If we put our mind to this, we could easily win this and do this. But I think the risk is, if this is not a priority for our nation to go after this and the other key enabling technologies of the future space economy, then we will lose, because they are doing it. It's just a question of whether we can and have the will to catch up and do it faster. So that's why I'm worried. I'm worried that it will just sort of be neglected while we focus on incremental improvements to the current stuff, when there's these huge opportunities out there that are really important. So I see them moving out on this right now faster than we are, and that does concern me, because I don't want the Chinese to dominate the future energy economy of the world. That's not a good future for us.
Do you see the mood improving on appropriations people in Congress to make sure you're getting, $250 million seems very light to me coming from the oil and gas industry. So, and it being one of your larger projects, talk a little bit about the future of those numbers.
Yeah, as Peter Gerritsen said, of course, it's a tiny, minuscule amount, but I'm thrilled we're doing something, honestly. So let's just be thankful that we do have some projects underway. And honestly, the early work is not super expensive. We have to mature these enabling technologies. What we need to do now is line up the next step, and the next step will be more costly and with higher payoff there. So I do, I do think that the recent emphasis on alternative energy sources and climate change are going to help us gain advocacy for this technology, because this is a super enabling technology to the future that everybody envisions. We just have to make it happen one step at a time. And I think I've got these near-term steps, but after that, it will need more support and more budgetary support could be in the private sector. So again, I'm kind of hopeful that something like that will ignite. Now, this conference is a great example of how we're trying to pull the ideas together in a way that will can then appeal to a larger audience about how important this technology is. And so I think the key ingredients are all there, and over time, I think this will be recognized as the great opportunity that it is. And I just want to be able to do my part in the near term to mature these things so that there's no technology showstoppers.
Great. Well, one last question from Dallas, who spoke yesterday. Really interesting conversations there. And Arachne, I love the name. It's great, a great match for SPIDR. What is the orbital positioning of Arachne, and what power density will be transmitted? And then how would that be diffused as it makes it down to the ground?
Yeah, so Arachne is going to be a ride share with another launch opportunity. So honestly, we're going to go to whatever orbit the host needs to go to, and that as long as it enables us to do our technology maturation mission. And really, we're pretty flexible on that. So it'll be somewhere in Leo, but just wherever the host wants to take us, that's where Arachne is going to be as this technology demonstrator. The details of the power density and how much expected power, some of that is still being worked out. Some of that I just am not personally familiar with those details, but they did assure me we could light up a small LED, and I said that's the minimum you have to do to prove the technology so people will believe this can work. But again, I think among the scientists, there's no doubt that the technology will work. I just want to also be able to have a little bit of a dramatic demonstration that can help, again, get resources for the next phase of development. So we'll light up an LED. That's my promise.
Okay. And we did get one more question tying back into the business plan competition. Can you talk a little bit about how this program can support a startup working in space solar power and the role of private enterprise?
Yeah, I think that's a really good question, because we do have Northrop Grumman is our prime contractor, was already selected to build the Arachne. That is the major line of effort here funding wise, but of course there's all these other enabling technologies too, and the various different smaller businesses are working on those. So there are multiple players already involved, and of course the question is how can new people get involved, and I think that is open for discussion. Well, as the current efforts kind of wrap up and mature, we'll be looking for new partners. And again, I think the key here is that this is not going to work if everybody's counting on it only being funded by the government. So we really need to find the right partnerships with NASA, with the private industry, and with the public-private partnerships. That's what's going to make the next phase of this go. And I think we should have some more discussion on what the right structure for that is. And then I am eager to do my part in the structure of that next level of development, whatever that ends up being. And I don't know what the right answer is there. I think we need some more discussion.
Sounds great. Look forward to following your progress and seeing those press releases. Thank you so much for being here.
Thank you so much for organizing the event and for the opportunity to be a part of it. Really appreciate it. I can't wait to go home and finish my High Frontier movie.
Yes, it's a good one. Those ending credit photos are wonderful.
Thank you.